Hey everybody, welcome back. This is part 2 of 3 in the lecture series about AlphaGo. Last lecture we talked about the state spaces of different games, and we saw that Go in particular has an astronomical state space due to its large branching factor. There are actually more possible board positions in Go than there are atoms in the universe. Because of this, mastering Go became a monumental challenge in artificial intelligence. People had tried to throw many different algorithms at Go, and none of them were able to find much success due to the enormous scale of the problem and the ingenuity required to be a skilled player. In 2014, a British artificial intelligence company called DeepMind began working on a project called AlphaGo, with the goal of creating an artificial intelligence that could beat the greatest Go players in the world. They did that in 2016 when AlphaGo defeated Lee Sedol, the highest ranked player in the world at the time, 4 games to 1. This feat was accomplished through a combination of learning algorithms, including deep learning neural networks, reinforcement learning, and Monte Carlo Tree Search. In the following 2 videos, I will talk about these algorithms. In this part, we will focus on Monte Carlo Tree Search, how it was adapted for AlphaGo, and how it differs from the general structure we talked about in the previous video. And if you haven't seen that video, I highly recommend it. I'll be piggybacking off of it for most of the video here. AlphaGo used Monte Carlo Tree Search as a way around Go's intractable state space, but there are some key differences in their implementation versus what I talked about in the last video. Instead of storing information in the nodes of the search tree, AlphaGo's implementation stores it in the edges, which represent actions. Each edge has an action value Q, which is kind of like our average value from the last video, a visit count N, and a prior probability P, which is new, and which represents the probability that a human expert player would choose the given actions from the given state. Now, we get these probabilities from outside of Monte Carlo Tree Search. They come from a neural network that was trained on many human expert games. In the selection step, the algorithm balances exploration and exploitation to traverse the tree. The exploitation term is equal to the Q value of the action. The exploration bonus is proportional to the prior probability of the action. The term also decreases as the visit count of the action increases to encourage exploration of less visited actions. The action that maximizes that equation is selected as the tree is recursively navigated until it reaches a leaf node. So how is this different from our example in the last video? The exploration term in that example simply depended on the visit count of the parent over the visit count of our child. The difference here is that we're depending on this prior probability P that we got from analyzing expert play with the neural network. When we have as large of a branching factor as we do for Go, this helps us select our moves more intelligently so we don't have to evaluate as many states. When the algorithm reaches a leaf node, it may choose to expand it, in which case it is evaluated using that policy network, returning prior probabilities P that are stored for each of the new actions. The newly expanded node is then evaluated using a blend of 2 values. One evaluation is a value returned by a neural network that takes in a board state and predicts the probability of victory. The other evaluation comes from a rollout using a simulation strategy. These are combined into one evaluation using a mixing parameter. So AlphaGo uses this value network where another algorithm might use a heuristic to try to estimate the strength of a position. The advantage of this is higher accuracy, but the disadvantage is that it's computationally expensive, much more so than a linear time heuristic would be. They were able to get around this by spreading the computation time across multiple machines. So they took a balance of higher accuracy in exchange for more computation time and more processing power. And finally, we have the backup step, which is similar to backpropagation from the last slides. Once the expanded node is evaluated, the result is backpropagated up the tree. Each action along the path that was taken in selection has its visit count incremented and its average Q value updated with the new result that we got from the evaluation step. So AlphaGo's implementation of Monte Carlo Tree Search is similar to what we talked about in the last video, but with the twist where it gets help from these neural networks. particularly that neural network that provides the prior probabilities based on analyzing the play of human experts. That helps identify moves that might be better in selection, just because there are so many possible moves in a game like Go. And then that value network that helps us evaluate states in addition to the Monte Carlo simulations that we talked about in the last videos. It does both of those to get a better composite valuation. So that's all for this video. Once again, I'm going to have my sources, just one source for this in the description. This is actually the AlphaGo paper that I based these slides off of. If you have any questions, feel free to ask them. I'll try to answer them to the best of my ability. And next episode, we're going to be talking about those neural networks, how they're trained, and what the thought process is behind them. So thanks, have a good day.